Hello everyone and welcome to this lecture on artificial neural network. Arguably, artificial neural networks are the most famous supervised learning algorithms and there are several reasons for the same. In today's lecture, we will explore multi-purpose algorithm and how we can implement it using Python. Let's have a recap of the previous content. In the last class, we discussed logistic regression. With that, we also try to understand the concept of decision boundary. We also saw one example and the Python implementation of logistic regression algorithm. In today's lecture, we will focus on the motivation behind artificial neural networks. We will learn about a very simple artificial neural network called the Perceptron model, and we will also try to explore the extended version of Perceptron model called multi-layer Perceptron. Artificial neural networks draw inspiration from the complexity and functionality of the human brain. They are primarily deployed for handling classification tasks across various domains. But they can also handle regression problems really well. What sets them apart is their remarkable ability to navigate through highly nonlinear decision boundaries, copying our brain's ability to make sense of complex and layered information. Throughout this lecture, we will explore the different architectures of ANNs, showcasing their adaptability in solving a broad spectrum of problems. In the last lecture, we discussed logistic regression, but there are a few limitations with this algorithm. First of all, it is difficult to come up with a sophisticated decision boundary when the corresponding data has non-linear structure. On the other hand, it is difficult to decide the appropriate fx beforehand, that is, even before applying the logistic regression algorithm. So if we have a very complex data set where it is very difficult to divide one class with the other and might need a decision boundary like this, logistic regression may not produce good results. In such scenarios, we rely on artificial neural networks which take their inspiration from human brain. So human brain is a very complex system, but in the end, we can say that it contains lots of neurons which process the information and maybe forward that information to the other neurons through axons. We have also components like dendrites, synapses in our brain. On the right side, we have a simplified version of neural networks. It is actually an artificial neural network. Here also we have these kind of artificial neurons which process some information, which receive information from other neurons, processes it, and forwards that to the next layer of neurons. So overall, the artificial neural network is a simplified version of the human brain architecture. Here, as you can see, there are lots of connections at this place and at this place. These connections also carry weights, which tells what is the weightage of the link between this neuron and this neuron. Ultimately, learning in artificial neural networks means coming up with the right values of the weights of these connections. Let's start with a very simple neural network having only one primary neuron which does some processing. This model is called a perceptron model. Let's see how this perceptron model works. So in the case of perceptron, we have only one neuron which takes data as input. So data, as you already know in classification, looks like x1, x2, xn and the corresponding y value. Here y is usually represented, once again classes are represented like 0, 1, 0, 1, where 1 may be yes, 0 might represent a no. We have added one extra term here called x zeros which has the value 1. This value is added in order to facilitate the constant term w0. We have similar structure already discussed in the logistic regression as well. So we have data coming from the input layer. Now each connection has a certain weight w0, w1, w2 to wn. Let's see what this perceptron does. This perceptron calculates this expression summation wi xi, which means w0 x0 plus w1 multiplied with x1 plus w2 multiplied with x2 and so on, wn multiplied with xn. Now, on the basis of this calculations, which is called fx in the end, this is how perceptron makes the decision. If fx turns out to be greater than equal to 0, we predict a 1. Otherwise, if the value of fx is less than 0, then we predict the corresponding value of y as 0. We can even go one step further. Rather than doing the decision making directly on the basis of fx value, which is ultimately the sum of wi xi's, we pass fx into a logistic function. If the logistic will give us the value greater than or equal to 0.5, then the corresponding value of the y would be 1, otherwise it would be 0. It is similar in the reasoning with when we have fx is greater than equal to 0, then the y would be 1. Because when fx is greater than equal to 0, then its logistic function would definitely be greater than equal to 0.5. But the benefit of using logistic function is that it restricts the value between 0 and 1, and we take the threshold in the middle 0.5. So whichever instance gives us value greater than 0.5, we predict this as 1, otherwise we predict that as 0. For convention, it is good to know that the place at where we supply the input values, we call in the nomenclature of artificial neural network an input layer, and the place where we make the final predictions, we call that the output layer. So on the basis of this fx, the predictions are made. That's why this becomes an output layer. This is a very simple perceptron algorithm. Let's say that the training data set has m number of examples. there are weights of the connections between input layer and output layer. We initialize their values randomly. Usually we start with a small random values, typically in the range 0 to 1. We set some alpha which represents the learning rate. Let's say in this specific case, alpha could be 0.1. We set another hyperparameter called max iterations, which tells us how many times these conditions are going to be executed. The common values of max iterations are 100, 500, 1000 and even 10,000 in many cases. And then we try to do the following reasoning. We first calculate the summation wixi value. If it turns out to be less than 0 and the corresponding actual class is 1, then we update the weight like this. And if the value of summation is positive but the corresponding class is 0, in that case we will reduce the value of weight using this expression, where I represents the number of independent variables and j could be any row of the available training data set. It is usually picked randomly. Let's try to do one example to understand the Perceptron algorithm in a better way. Let's say we have been given this data set. We can represent this using the simple architecture of Perceptron. Here we have two inputs, x1 and x2, but we have added one more term, x0, the value of which is 1, to support the weight w0. The weight corresponding to x1 is w1 and the weight corresponding to x2 is w2. So our fx becomes w0 x0 plus w1 x1 plus w2 x2. Let's say we initialize with these random values of w0, w1 and w2. So w0 is 2, w1 is 5 and w2 is 3, and our alpha is 0.1. So we do the calculations like this. Let's say we consider the first row and we first try to calculate what is summation wi xi. So x0 is 1, x1 is 2 and x2 is also 1. When we put these values here and we have started with these random values of wi's, it turns out that the summation is 15. Now since the summation is greater than 0 but the corresponding class y is 0, which satisfies the second case of the iteration, in that case we will reduce the values of wi's like this. W0 in this case is w0 minus alpha times x0. We know that x0 is 1. Similarly, w1 is w1, the previous value, minus alpha times x1, which is 2, and x2 is once again 1. So when we update it, we got these values of w0, w1 and w2. We once again take the second row this time. We do the same calculation with the updated values of w0, w1, w2, and it turns out to be 22.1. This is our x0, this is our x1, this is our x2, which we have taken from the second row this time. Now we know that the corresponding class is 0, but the summation turns out to be greater than 0, which means we once again follow the second criteria of our loop, and we have to further reduce the value of wi's. Then we consider the third row. This time the summation is greater than 0 and the corresponding class is 1. Now there is no such criteria when the actual value should be 1 and the sum of wixi should also be greater than 0. There is no such criteria. That's why we will not do the updation in wi's this time. The one which make changes is when y is 1, then summation should be less than 0. But this is not the case in our situation. We have y is equal to 1, but the summation is greater than 0. That's why we will not do any updation. And the same is true for the fourth example as well. In this case also, even though the y is 1, the summation is not less than 0. It is rather greater than 0. That's why once again we will not do any updation. So when we are done with the first iteration, our wi's have been updated to these new values. When we repeat that multiple times after several iterations, which is given by the parameter max iterations, we will find that after reaching to these values, the values of wi's are not changing further. They have reached to a saturation point and we will stop at this point as well. Once again, like logistic regression, if we put w0 plus x0, which is 1, plus w1 x1 plus w2 x2 to 0, then x2 can be written in terms of x1, which means it gives us a curve like this. This curve, our fx being 0, is actually the decision boundary, and its behavior is also similar to what we have seen in the lecture of logistic regression. This region here represents fx greater than 0, and this region here represents fx less than 0. So for a new instance, we will put that in this expression. We already know the value of wi's by now. If fx turns out to be greater than 0, which represents that the point is above the decision boundary, hence we will predict it like the blue ones. If it is below the decision boundary, then it belongs to the red points. Before we move forward and discuss more complex form of artificial neural networks, it is important to consider linearly separable data set. So a data set is called linearly separable if that data set can be separated by a linear combination of independent variables. In 2D, it looks like this line. This line actually is the linear combination of independent variables x1 and x2. In 3D space, it looks like a plane, which is the linear combination of three variables x1, x2 and x3. This statement is true for multiple dimensions as well. That is, the number of variables could be 4, 5 or even more. But if we can separate the two classes with the help of their linear combination, it will come in the category of linearly separable data set. On the other hand, we have the concept of linearly inseparable data set, which means if a data set cannot be separated with a linear combination of independent variables, then it is called a linearly separable data set. So if we have this data set of two variables, x1 and x2, and red and blue here represents two values of y, maybe 0 and 1. In that case, no linear combination of x1 and x2 can separate blue points with the red points. That's why it falls into the category of linearly inseparable data set. We are discussing this because there is a limitation of Perceptron algorithm, and that is it can only classify the linearly separable data set, or in other words, it cannot classify linearly inseparable data set. In that case, we resort to much complex combination of perceptron, which is called multi-layer perceptron. It is actually a typical artificial neural network. We can say that multi-layer perceptron is an architecture of many simple perceptrons put together. The benefit of considering this architecture of perceptrons is that it can now classify linearly inseparable data sets as well. So in this specific case, if we focus only on this point, it is a typical perceptron structure where this represents the input layer and this specific neuron is the output layer. However, we have taken more perceptron. This is the output layer, you can say, of the simple perceptron network. We have considered another perceptron, and we have also taken one extra by stem here, very much like this stem which we introduced by ourselves. And we take their results and combine to the next layer of perceptron, which gives us finally the predictions corresponding to the actual values y. In this specific structure, you can see that there are two sets of weights. One set is between the first input layer and this middle layer. In the literature, we call this the hidden layer, and this becomes the output layer. And then there are separate weights between hidden layer and output layer as well. This is a very typical structure of multi-layer perceptron network. Now it is important to understand a few terminologies here. First of all, hidden layer. The additional layers between input and output layers are called hidden layers. There could be one hidden layer and multiple hidden layers as well. Majority of the computation that typical neural networks do, it takes place at these hidden layers, because input layer just supply the input, output layer does the final prediction, but these are the hidden layers that do most of the computation. On the other hand, at each neuron, especially at hidden layer, a special mathematical operation is applied called activation function. What it does is it transforms the input signal coming from the previous layer and converts that into the output signal. It helps the network learn more complex patterns in the data. There are many activation functions available in the literature. Some commonly used are linear, sigmoid, and hyperbolic tangent. Now, multi-layer perceptron, they use a very specific algorithm called backpropagation algorithm. What this algorithm does is it adjusts the weights of the neural network. How it does that? It first calculates the error at the output layer and sends that error back to the hidden layer in order to adjust the weights of the neural network. The weights are adjusted on the basis of the amount of error between the actual value and the predicted value. Let's try to understand that. Let's say I have this neural network architecture where this is my input layer, this is the only hidden layer I have, and this is the output layer. Let's say I take some typical example of x1, x2 and y. This is 2, this is 3 and the corresponding classes, let's say 1. We already have this data. So when we supply 2 here, 3 here and 1 here, calculate values here, then once again calculate values here also, combine them and calculate finally value at this point, maybe the value turns out to be 0.5. Remember, there are weights on each edge here and here as well. So, as we can see that the actual value is 1, then the difference between the predicted value here 0.5 and the actual value 1 is 0.25. So corresponding to this amount of error, the weights are adjusted first at this point and then at this place. As you can see, it is a combination of 2 steps. The first step is the forward step where we calculate the predictions and calculate the error between the actual values and the predicted values, and then we send the error back in order to adjust the weights of the neural network. This is how the typical multi-layer perceptron algorithm works. So this is a very technical algorithm for multi-layer perceptrons. Some steps are similar to the perceptron algorithm. This step is called the feed forward step, where we actually calculate the amount of error, and these whole steps, they are called back propagation step, and according to that we update the weights between the hidden layer and output layer, and finally the weights between input layer and the hidden layer. I have removed the subscripts here, but often we represent I to represent the index of hidden layer neurons, J or sometimes H to represent the numbering of neurons in the hidden layer, and K or O sometimes to represent the number of neurons in the output layer. Like any other algorithm, once you have made a neural network, trained it, then the next obvious step is to test the performance on unseen test data. Now, if the performance is not satisfactory, we have to either change the number of hidden layers, the number of neurons in a hidden layer, or maybe the learning rate. So with that, we have discussed perceptron model, which can handle the linearly separable data set only. And then we have an advanced version of Perceptron called multi-layer Perceptron model, which can handle linearly inseparable data set as well. Now we will discuss the Python implementation of multi-layer Perceptron model. Thank you. Hello everyone, and let's try to implement the multi-layer Perceptron algorithm using Python libraries. So as you can see on your screen, I have already mounted my drive. Then I will run the important libraries needed to implement the ANN algorithm here. So as you can see here, MLP classifier is the multi-layer Perceptron classifier. Now I will read data. I am using the same iris data with 3 classes. Let's check the data set size and its shape. So as you can see here, we have 150 rows and 6 columns. 150 means 50 for each class. The iris setosa class, the versicolor and virgilica class. Let's also do the counting for each class. So as you can see, each class has exactly 50 instances. Once again, like in the previous case here, we need to drop the ID column because it does not impact the prediction. After that, as you can see, the species column is of text nature. It is a textual, it provides a textual information. So we need to convert that into numbers once again, as we did in the case of logistic regression. Once we do that, then a number is assigned to each of these classes. Once again, we need to drop a species column now because we have this new column with the name species encoded. So once we do that, we have all the pre-processing. We have removed the ID column, and we have also added this extra column where the class is numeric in nature. Finally, we will arrange our data into X and Y, where X represents the matrix of independent variables and Y the column vector for the class to be predicted. Let's divide our data set into train and test now. Let's see the data set size for training and testing. So training set has 135 instances and testing data set has 15 instances. Now using this very simple function, we can create a model of MLP multi-layer Perceptron, and then we will supply our training data X train and Y train to fit the data. After doing that, next step is to predict the model's performance on the training data set first. So as you can see that the accuracy we got is around 97% on training data set. Let's check the accuracy on testing data set also. And in this case, the testing accuracy is around 93%. Though we took a very simple multi-layer classifier function here, but in fact it contains lots of parameters that need to be defined. So if we want to, we can create our own specification of MLP classifier. As you can see here, we can set how many hidden layers we want. So in this specific case, I have mentioned 2 hidden layers. The first hidden layer contains 10 neurons and the second hidden layer contains 5. The number of epochs or maximum number of iterations are 500. The activation function that I am using in the hidden layer are logistic function. The optimization algorithm used is stochastic gradient descent, SGD. I have initialized the learning rate with 0.01 and the learning rate will remain constant with each iteration. We can also mention adaptive types of learning rate, where learning rate changes as the iterations increase. I am calling it the new model. So once run, we have created a new model of MLP classifier with these details. Now let's try to fit the same training data on this new model. So we will use new model dot fit and pass the training data. So the classifier has been created. Now let's do the predictions. When we run this, as you can see here, that the training accuracy even has been reduced from 97% to around 69%. Let's check the testing accuracy. The testing accuracy has also been decreased and it comes down to 60%. So we can say that the model of multi-layer perceptron that we just created is not a good model. We need to change its parameters and update it, and maybe then the training data can be fitted in a better way and its performance can be increased on unseen data like X-test. Let's try doing it. So apart from changing all the parameters, what I'm doing right now is I'm considering only one hidden layer with 10 neurons in that. So I have removed the second hidden layer. Let's run this once again to update the model. Once executed successfully, the new model now contains only one hidden layer with 10 neurons and rest of the parameters will remain same. Now fit on this newly created model with one hidden layer. Predictions on training data set. You can see that the performance is improved once again to 97%. In fact, rounded off to 98%. Similarly, if we check the performance of test set, it has also been increased to 93%. So in this way, you can see that coming up with the right architecture of neural network is an empirical process. What do we mean by that is we need to keep on changing the values of the parameters. We call them, by the way, hyperparameters. Soon we will discuss what is the difference between simply the parameters and the hyperparameters. But we need to change the hyperparameters. We need to sometimes change the activation function. Sometimes we need to change the learning rate. Sometimes we need to add or remove extra hidden layers and then keep on testing the newly created models on the training data set. That's why coming up with the right structure of the MLP classifier is a highly empirical process and we need to try different combinations. But I hope this session gave you some idea of how you can implement your own MLP classifier. Thank you.